Okay, hello everyone. Welcome to week 7 live session of uh, NPTEL's Introduction to Semiconductor Devices course. I'm Om Maheshwari and today we will solve some questions that will help you with your assignments as well as your exams. So before getting into the questions, let's give me a moment. Okay, so let's start with a quick recap of the slides from the course so you can follow the lecture better. So in this week, mainly we'll be looking at the MOS capacitor and its related properties. So from this week 7 to till week 10, these are like the most important topics of this course. So I request you all to please uh, see the lectures and prepare well. And because if you want to join any of the semiconductor industries, these topics are the most important ones, covering the MOS physics. Okay, so let's go through the slides once. So this is the energy band diagram of a MOS capacitor. So we have seen this in the last lecture also. So this is just an energy band diagram in the uh, flat band condition. Right? The bands are flat, and this is the Fermi level. So here we are just calculating the work function difference. For ideal MOS devices, work function difference is 0. That is, work function difference is phi m minus phi s, where phi s includes this this difference and this difference. Work function differences from vacuum level till Fermi level. What is the energy? That is work function difference. That is the work function, and the difference between the work function of the metal and semiconductor side is called the phi ms. That is the difference of the work function. Phi m minus phi s. For ideal MOS, it is 0. We are assuming the work function of the metal and work function of the semiconductor is exactly the same. Okay. So work function in the semiconductor side, you can see this will be this chi, that is 4 eV, plus Eg by 2. This is Eg by 2, and this is phi f, right? Fermi potential, that is Ei minus Ef. Okay, so now in accumulation, as we have seen, when you apply, so assuming a n-type MOS capacitor, if you apply negative voltage, that will increase the potential on this metal side. If you apply negative voltage on the metal, the bands will bend like this, and holes. So this is a p-type substrate. So holes will be attracted here at the surface, right? So if you see this chart diagram, you have a negative Q here and a positive Q here. This is due to the holes at the interface. And the electric field is something like this. That is a constant electric field in between the in the oxide, and it's 0 throughout. And this is how the potential diagram will look like, which is almost the opposite of this. In depletion, when you apply a small positive voltage, positive Vg to the gate, your bands will, so it will shift downwards. The metal Fermi level will shift downwards, and your bands will bend downwards. Right? So you're depleting the electrons depleting the holes from here. So holes that were there, they have depleted, and there is immobile ions now near the surface in the depletion region. This is the chart diagram. You have like a positive charge at the gate and the negative charge in the depletion region in the semiconductor. This is how the electric field is looking like. This is the electric field, and this is the potential plot. So here now you will have some surface potential. Surface potential is nothing but this is surface potential psi s, right? This difference is surface potential. So your Vg is some voltage drop in oxide Vox plus psi s. Vg is Vox plus psi s. Okay, so right, psi s is shown right here. We can also see this is psi s, this is psi s. This is the Fermi potential pi f kT by q ln ny ni, and okay. So in inversion, inversion is when you have applied a larger positive voltage, and in inversion, what happens is in inversion your psi s equals to 2 times phi f, right? This is the essential condition, that so that you are inverting the channel. What it means is you are the this was a p-type substrate. Now you have brought in equal number of electrons here at the surface, equivalent to the number of uh, holes that were there in the bulk, right? So that essentially you have inverted the channel. So let's say if your bulk was doped 10 to the power 15 uh, per centimeter cube, and then so when this becomes the concentration of electrons at the channel becomes 10 to the power 15, then the channel is inverted, right? So this inversion, so that only happens when psi s equals to 2 phi f, right? Why 2 phi f, you may ask? Like, one of the phi f is just to go to intrinsic part to repel the holes, right? So that you have an intrinsic, then another phi f, that is this one. Another phi f is to make it to bring the equal number of electrons, right? So that's why it is 2 phi f. So here now you have this depletion charge as well as the electrons at the surface. So this is how your electric field, and this is your potential. So the potential in the oxide is linear and like quadratic kind of behavior in the semiconductor. When you gate charge, this Qg will be equal to this Q inversion plus Q depletion. The relationship between Vg and psi is Vg equals to Vox plus psi s. So by solving this, finding Vox is epsilon ox Dox, then epsilon is equal to epsilon Si ESI and by Eox and Q NaW by epsilon. So all this you do, you find that it is Vg is minus Q depletion by Cox plus psi s. So this we have seen. Okay, so Vg is so minus Q depletion by Cox. So this Q depletion is Q NaW plus psi s, and your depletion width is under root 2 epsilon Si by Qna into psi s. This you can find uh, by the we have already found this in the previous class using the Poisson's equation. So if you replace this W here, what you get is this Vg is minus under root 2 epsilon Si Qna psi s plus psi s by Cox. So if you draw this psi s versus Vg, you get this kind of graph. So this Vg is for here, this relation is here, right? And here it saturates, here it also saturates. And why does it saturate? Because you see, once you are increasing psi s, right? Once you are increasing Vg, what starts to happen is your Qd increases. Then after inversion, what happens is all your voltage drop tends to happen in the oxide, and very little voltage goes to the semiconductor. And why this happens is because in a MOSFET oxide, this is semiconductor. So once you have an inversion layer of electrons, so what will happen is whatever electric field you apply, it will be shielded by this layer of electrons, the inversion layer. So most of the potential drop will start happening in the oxide, and psi s will almost saturate. Psi s will increase very slowly. So this is why if you draw psi s versus Vg, it looks something like this. In both of these cases, you have a channel of holes, electrons. Here you have a channel of holes, which are shielding. And here only in the depletion, your psi s and Vg are increasing. So the voltage at which the surface inversion happens is called the threshold voltage, and the condition for surface inversion is psi s is equals to 2 phi f, and the voltage at that point is you just replace here 2 phi f, 2 phi f. This is your then it becomes a threshold voltage. And if you want to see psi s versus q, so in this x-axis you have psi s, in y-axis you have the charge, semiconductor charge. So in inversion, it uh, it is exponential as you keep on reducing psi s to negative value. It is exponentially dependent, minus phi s by 2 kt, exponential. And in depletion, it increases by square root dependent. We also already saw it. So Qd is 2 epsilon Si and Q psi s, right? 2 epsilon Si Qn Si. This is your Qd. So it is square root dependence, and inversion charge is again exponential. It exponentially rises. So finally your charge becomes this. Exponentially it rises, exponential Q by Kt, right? 2 Kt. So in inversion also charge exponentially rise. For very small change in psi s, your charge increases inversion charge increases exponentially. And these are the diagrams, charge block diagram we have already seen. In accumulation, you have positive holes at the surface. In depletion, you have depleted negative charge. In inversion, you have depleted negative charge plus the channel of electrons. Okay. So Right, this just shows you what is psi s versus uh, how your transition. So at psi s equals to 0, this is flat band condition. Psi s is negative, you have accumulation. As psi s positive, you have depletion and inversion. Psi is equals to 2 phi f, or inversion happens, right? Where phi f is kT by q ln Na by Ni for NMOS. And the similar thing, exactly opposite, is in PMOS. Everything is just negative. Okay, and your threshold voltage is Vt is equal to epsilon Si Q Na psi s upon Cox plus psi s. Or I should write 2 phi f plus 2 phi f. This is your threshold voltage. Alright, so let's take the questions now. So the question is, a MOSFET is said to be in inversion when dash carrier concentration at the surface equals or exceeds the dash carrier concentration in the bulk. So to solve this, you again imagine a MOSFET, metal, oxide, semiconductor. Let's say it's a p-type. For an n MOSFET, your substrate is p-type. So your majority carriers here are holes, right? And one inversion happens when you apply a positive voltage, Vg greater than Vt, then a channel of electrons is formed here, right? So, but electrons are minority in p-type semiconductor, right? So, MOS is said to be inversion when minority carriers at the surface, carrier concentration at the surface equals or exceeds the majority carrier concentration in the bulk. Okay, so the answer would be option B. Okay, so let's see the next one. So in this question, you have been asked for a mass capacitor in strong inversion, the surface charge density should be dash with surface potential. So we know for inversion, we saw that, right? Psi s equals to, okay, in inversion, if you remember this graph, it increases exponentially, right? This is inversion from here onwards. All this is inversion. So in inversion, your charge at the surface of the semiconductor increases exponentially. It will work 5 by 2 kt. So the answer should be increases exponentially, right? Here, Q inversion proportional to exponential. Right? This is the relation for the charge. Can be seen from that curve, right? I versus Q semiconductor. This is accumulation, depletion, inversion. In inversion, it is exponential Q psi s by 2 kt. In depletion, it is under root Q Na epsilon and psi s. Here it is again exponential minus Q psi s by 2 kt. So in inversion, it is exponential. Next question. Okay, so let's see how this question goes. In a MOS capacitor, inversion is achieved when options are the surface potential equals the applied gate voltage. The surface potential is greater than or equal to the twice the Fermi potential. The depletion region is fully depleted. The gate voltage is negative for an N-type substrate. The answer is no, right. In inversion, we have psi s equals to 2 times phi s, right? Which is this. So next one, a MOS capacitor can be represented as option A, two constant capacitors in series, B, two constant capacitors in parallel, C, one constant and one bias dependent capacitor in series, D, one constant and one bias dependent capacitor in parallel, and E, two bias dependent capacitors in series. Okay, so if you remember, in our MOS cap, what we have is we have metal, oxide, and semiconductor, right? If we apply, let's say, VG here and ground here, we have psi s at the surface, and this oxide gives us a capacitance here, and we have, when we apply some forward bias, we have a depletion capacitance here, right? So depletion charge here. This is also kind of acts like another capacitor, right? CD. So equivalent diagram would be Cox CD. Here you have applied VG, and here your potential is psi s. Right now, Cox is a fixed capacitor that depends on the thickness of the oxide, right? It is epsilon ox by Tox, so it is not VG dependent. But CD depends on psi s, right? Because CD will be epsilon silicon by WD, and WD is dependent on 2 epsilon psi s by QNA, right? Well, WD is psi s dependent. So your CD is voltage dependent, bias dependent capacitance. So you have one fixed capacitance, one bias dependent capacitance, both are in series. So answer to this will be option C. Okay, let's look at the next question. Please try to think about it. Okay, so this is a very simple question that you all have answered. So the question is, what is the typical thickness of SiO2 layer in modern CMOS technology? So in modern CMOS technology, the SiO2 thickness is between 1 to 2 nanometers. Yeah. Next question, for a P-type MOS capacitor, increasing the acceptor doping concentration will do what? Sorry, this should be N-type. It's a typing mistake from my end. So we read it as for an N-type MOS capacitor, because acceptor doping will be an N-type MOS capacitor. So for an N-type MOS capacitor, increasing the acceptor doping concentration will increase the threshold voltage, decrease the threshold voltage, have no effect, or reverse the type of inversion. So in N-type MOSFET, you have metal oxide, then you have semiconductor, which is P-type doped Na, right? So what is the threshold voltage? We have seen that Vt equals to minus Qd by Cox plus Is, right? So here it will be 100 to epsilon Si Q and 2 phi f plus 2 phi f upon Cox, right? So this is your threshold voltage. So let me just erase this for confusion. Okay, so if your substrate doping Na will increase, your Vt will also increase, right? So if Na increases, your Vt will also increase. Further, your 2 phi f is also increasing, right, with Na. So phi f is Kt by Q ln Na by Ni. So if Na increases, phi f is also increasing. So both of these factors are increasing Vt. What does this mean? To bring the uh, in a higher dope semiconductor, to bring the same surface potential, you need larger Vg. Okay, next one. Please try to solve this. solve this question. So the question says we have a MOS capacitor and with an oxide layer thickness of 10 nanometers and the depletion layer thickness is 100 nanometers. The permittivities of semiconductor and oxide are epsilon s and epsilon ox. Assuming epsilon s by epsilon ox is 3, what is the ratio of the maximum capacitance to the minimum capacitance of this MOS capacitor? Okay, so if you remember one model, right? So with this CD and COX, so Cmax will be capacitance will be maximum only when we have COX, right? Because so this is in series, it will be 1 by your CG will be, well, rewrite it. So CG will be 1 by COX plus 1 by CD. Okay, so actually that is C semiconductor. So it will be maximum when 1 by CG, sorry, will be equal to COX when this psi s is, let's say, um, 0, right? When there is no charge in the semiconductor, so this will not come, only we will have COX. And CG will be minimum when both of them are coming. So let's say depletion case 1 by COX. Okay, so if you take the increment, it will be COX into CD by COX plus CD, right? Depletion only. Okay, so this is your minimum capacitance. So we have to find the ratio of, to find COX, sorry, we have to find Cmin by Cmax. Sorry, you have to find Cmax by Cmin. So it will be COX by COX CD and COX plus CD. COX will can answer Cmax by Cmin plus COX plus CD. Okay, COX. COX by CD plus 1, right? And it should be equal to epsilon ox by TOX by epsilon S by WD plus 1, which is epsilon ox by epsilon S into WD by TOX plus 1. Epsilon ox by epsilon S given 1 by 3. WD is 100, TOX is 10 plus 1. It is 10 by 3 plus 1, which is 3.33 plus 1, which is 4.33. Right, so answer is option A, 4.3. Okay, let's see the next one. Solve this. Okay, so let us see how this question goes. It's a very easy question. I hope you all have solved it. Question is, the energy band diagram of MOSFET device is sketched in this figure. Assume that the electrostatic potential is zero in the semiconductor bulk, that is at large distance from SiSO2 interface. There is no metal semiconductor work function difference. These are some values. We have to find what is the value of phi f. So we know that phi f is Pi at bulk minus Pf, right? So this is exactly phi f, which is 0.3 electron volts. So answer is option yes, 0.3. Next question. So for the same diagram, what is the applied voltage at the gate? So first of all, you see this is a P-type substrate, right? And that means it is a NMOS. Okay. And you see bending is downward like this. So bending is downward means it is in depletion, and depletion will happen only in positive voltage. So the voltage applied Vg is positive. Now, how much Vg it's supplied is this. So you can also see here from EF initial, let's say EF metal initial, it would have been in the flat band condition. You have gone down. When you are going down, you apply positive Vg. Okay, so your Vg applied is 0.6 volts. Next one, what is the doping density Na in per centimeter cube? So this we can find from this phi f, right? Because phi f is Kt by Q ln Na by Ni. So Na will be Ni exponential Q phi f by Kt, which is 10 to the power 10 exponential 0.3 by 0.026. So if we solve it, Na will be 1.02 into 10 to the power 15 per centimeter cube. So this is option A. Okay, next question. What is the significance of the flat band voltage in a MOS capacitor? Option A, it represents the voltage required to achieve strong inversion. It is the voltage at which surface potential is zero. It is the voltage at which oxide capacitance is minimized. It corresponds to the threshold voltage. Yes, so it will be the voltage at which surface potential is zero, right? Its name is also flat band. Flat band means your bands are flat. Metal oxide semiconductor. So bands are flat. That means there is zero surface potential. Okay. So see the next one. Given a P-type silicon MOS capacitor with doping concentration Na, the permittivity of silicon is this. Calculate the maximum depletion width when the surface potential reaches 2 phi f, where phi f is the Fermi potential. Assume phi f is 0.3 volts. So we have to find maximum W depletion width when phi f is when psi s equals to 2 phi f. What is WD? WD is under root 2 epsilon Si psi s by Q Na, right? And WD max is when psi s equals to 2 phi f. So WD max will be under root 2 epsilon Si 2 phi f by Q Na. Now if we substitute the values, it will be under root 2 into 11.7 into 2.85 into 10 to the power minus 14, 2 into 0.3 more divided by 1.6 into 10 to the power minus 19 into 10 to the power 17. Okay. So when you solve it, you get 8.8 into 10 to the power minus 6 centimeter, which is equals to 88 nanometers. Just this last option D. Okay, next question. For the charge block diagram of the semiconductor shown below in this figure, what is the correct electric field plot corresponding to the given charge diagram? Okay, so you have in this question a negative charge at the gate and a positive depletion charge in the semiconductor. That means it must be a PMOS, right? In PMOS only you will have N-type substrate, and N-type substrate will have Nd plus ions in depletion, donor ions in depletion. Okay, so in PMOS when you apply negative voltage, you will have this. Okay, so electric field will be to start from negative and go to positive, right? To zero and then zero. So it will be option C, because electric field is in positive to negative direction, right? So it must be, and it is opposite to direction of x. So your electric field must be negative, so which is in option C, and it will be constant here and decreasing like this here. All right, let's take the last question for today. For the same semiconductor charge block diagram, you have to find what is the corresponding electrostatic potential plot. Okay, so if you remember, your electric field plot was something like this. This is oxide. This was your electric field, right? So potential is integration of electric field, right? So it will be option A. Integration of constant will be linear. Integration of linear will be quadratic. So option A is correct. Okay, so this was all for today. So if you have any questions, please feel free to email me, and I'll see you next week at the same time. Thank you.